Sketch a graph satisfying the following conditions. Let's draw a coordinate system to see what this is about. You have f of -2, so 1, 2, that's -2, and let's say this is -1. If f of -2 is -1, then the graph must be passing through this point, -2, -1, right? Now, then you have f of 2, 1, 2, and that's also -1, so it must be passing through this point. And then f of 0 is 1, so if I say this is 1, f of 0 being 1 means it passes through this point. So you're looking at a graph that passes through these 3 points. That just satisfies all the first line. Let's go to the second line. Here it says that the slope of the tangent line at these 3 points that we just picked are all horizontal. Now you want to think about what it means for the slope of the tangent line to be horizontal. There are actually 4 possibilities. A graph that's curved like this would have tangent slope 0 right here, or it could also be like this. In other words, if you have a relative minimum or relative maximum, then it's possible to have a slope 0 tangent line. But it could also be like this. So one example of this is y equals x cubed. That one has 0 tangent line, slope 0 tangent line at 0. So the tangent line pierces through the graph at this point. Or it could also be going the opposite direction. It's also possible to have a tangent line to have 0 slope. Okay, so you have these 4 possibilities. And then since we can't decide which one we need, let's go to the next line. And we see that between before -1 and after +1, f double prime is positive, meaning that it's concave up. So remember, if the second derivative is positive, then it's a smiley face, it's concave up. So we know that it's this case. Okay, so we know that over here at -2 and also at +2, because they both satisfy this condition, -2 is less than -1, 2 is bigger than 1, so it satisfies this condition. And then over here, -1 to 1, f double prime is negative, meaning that it's concave down, right? Concave down. So it must be this one right here. Okay? And then to satisfy that for the entire interval between -1 to 1, you would want to have it concave down, and then over here it should change to concave up. Right? It should change to concave up. So it satisfies everything here. Okay, so that's the graph. That's the answer for part A. Alright, now let's move on to part B. Determine the relative minimum and maximum values of fx using the second derivative test. Well, the second derivative test, see, f double prime of 0 is negative, because when x is 0, it satisfies this, right? So that means at x equal to 0, since f, so actually let's write both. F prime of 0 is 0, that we know. Right? F prime of 0 is 0, and then f double prime of 0 is less than 0. That means by second derivative test, let me erase all this. By second derivative test, you have second derivative test, x equal to 0 is a relative maximum. Okay, because if it's a frowning face, the point where the slope is 0, that's the top, right? So think about the frowning face right here. It's the maximum, okay? And then let's move on. If f double prime of -2, well, -2 is less than -1, so we know that f double prime is positive. And we also know that f prime of -2 is 0. So the second derivative test says x equals to -2 is a relative minimum, because if you have a smiley face when the slope is 0, that point is a minimum, right? Okay, let me erase some other stuff here. And then finally, f double prime of 2 is also greater than 0, and f double prime of 2 is 0. So this means second derivative test says x equals to 2 is a relative minimum. Okay? So these are all the conclusions you can draw for a second derivative test. Okay, now find the inflection points. Well, inflection points are when you have -1 and +1. So x equals to 1 and x equals to +1. Actually, x equals to -1 and x equals to +1 are inflection points, because that's when the concavity changes, right? And then what else? Oh, we need to know where it's concave up or concave down. Well, basically this is concave up and this is concave down, right? So you can say the following: concave up on the interval -infinity to -1 union 1 to infinity, and concave down on -1 to 1. Okay? Okay, next question. Fill in the table and use the table to graph y equals to f of x. Label any points of inflection and relative extrema. Okay. Alright, first, if f of -1 is -4/3, that means the graph passes through -1, -4/3. If f of 0 is 0, then the graph passes through 0, 0. Now, if f prime is negative, that means f is decreasing. Okay, and then if f prime is positive, then f is increasing. F double prime negative, remember, second derivative negative means it's a frowning face. That's called concave down. So f is concave down. And here it's the opposite. That means f is concave up. And again, it's concave down. Now, if the limit as x goes to positive is 3, that means y equals to 3 is a horizontal asymptote. Okay. And in the same way, if you send x to -infinity, you get 0. That means y equal to 0 is a horizontal asymptote. Okay, so let's draw the graph using all this. Let's see. So first, let's just make sure that we know the shape of the graph. You have this -1 and positive, before -1 and after -1. So let's say this is -1, and f prime is negative before -1, and positive after negative 1. Okay. On the other hand, f double prime changes its sign at negative 2 and also 0, and f double prime is negative before and then positive after and then negative after. Okay. Yeah. Just so that we don't get confused, let's put negatives for everything here, and then plus everything here. Okay. So what does that mean for our function? Well, for our function f, this is decreasing and it's a frowning face. So look at the frowning face. It's this right half side is decreasing, right? So we take that portion of the graph. So the graph is going down like that. Okay. And then it's decreasing and it's a smiley face. So it's decreasing but it's part of a smiley face. Increasing, so it's the other side of the smiley face. And then it's increasing but frowning, so it's increasing but frowning. Okay. Make sure that it's increasing. If you go like that, that's decreasing afterwards, so that's wrong. Okay. All right. So that's the graph, and now we will have to put everything together. So let's draw the coordinate system. I know that it has to pass through 0, 0, and negative 1, negative 4/3. So negative 4/3. Let's say it's this point here. Okay, so it has to pass through these 2 points, and also here's 1, 2, 3. At 3, you have a horizontal asymptote, and also at 0, you have a horizontal asymptote. Okay, and then here's negative 2. So before negative 2, what happens is the graph must be going down like that, right? And then it has to continue to go down up till here. So this takes some thought. Okay, so it's not as straightforward as it seems to be. I'm doing this seemingly very easily, but try to see why I'm doing that. See, first, the graph has to be shaped like this before negative 2, but as you go further to the left, it has to get closer and closer to this red line, because that's the asymptote as x goes to negative. So you really need to draw the graph like that. But you don't want to go down too much, because then after that it still has to go down, and then it has to go down to this negative 1, negative 4/3. So at most it goes down here. Okay, and then it has to go up because between negative 1 to 0 it has to have this shape, so that you have to connect these two using this shape. And then afterwards, after 0, it has to be shaped like this, and it has to get closer and closer to this y equals to 3. This is right at 3. So it better be going like that. Okay? So that it does have this y equals to 3 as the asymptote. Okay? So we have that, all that, and label any points of inflection in relative extrema. Okay, so this point right here will be relative minimum at negative 1, negative 4/3, because that's the minimum, right? And there are 2 inflection points. So this will be one inflection, which is 0, 0. And this one is another inflection, but we don't know what the y coordinate is because it's not given in the problem. So it's an inflection at x equals to negative 2. That's all we know. We don't know the y coordinate. And that's it. That would be a perfect graph. Now the graph of y equals to fx is shown below. Right? What is the domain of this function? Well, domain is all the possible x values, right? So you can evaluate f of negative 4. For example, f of negative 4 is slightly less than negative 5, right? And you can evaluate f of 7, right? You can even evaluate f of 1. F of 1 will be 0 right here because that's the closed circle. You don't use this open circle value. You use the closed circle value, so f of 1 is 0. But beyond negative 4 and 7, you don't have a value. So for example, if you wanted to know what f of negative 5 is, there's no graph there. Same thing, after 7, the graph is non-existent. So we see that only values between negative 4 to 7 are allowed. That means the domain, in our case, is negative 4 through 7. And because the endpoints are included, we put square brackets in both cases. We put the closed interval. Now, if any one of these were open circles, then you would put the open interval, which means it has to be round, right? So if this was open, just like this, then the right side will be like a round bracket, and if this was an open circle, then the left side would be the round one, the parenthesis one. All right, what are the critical numbers? Also, for each critical number, determine whether it is a relative maximum or relative minimum or neither. Okay, so first, remember, critical numbers cannot be endpoints, so endpoints are excluded. These are points where f prime is 0 or f prime does not exist. Okay. Now, f prime is 0 if tangent slope is equal to 0. Okay, and f prime does not exist. Actually, the derivative may not exist for two reasons. Number one reason is not continuous. Number two reason would be it has a sharp turn. Sometimes called a corner. I don't see any corners in this picture. I do see a point that's discontinuous. So to get a critical number, it has to be either one of these two cases, and therefore we see that right here when you have horizontal tangent, right here where f prime is not defined, those are the two critical numbers. So the critical numbers are -1, that's the x value. Critical numbers are numbers on the x-axis, so you don't put the y coordinate. So it should be -1 and +1. Those are the two critical numbers. For each critical number, determine whether it's a relative maximum, relative minimum, or neither. Well, this one is clearly relative max. So -1 is relative max because it's the highest point among the nearby points, right? And this one here is, well, let's try to see clearly. So let's think about what this point is. Well, if you take the neighbor of 1, so nearby points, then you only have this portion of the graph and that portion of the graph, okay? And as you can see, among this portion of the graph, this point is the lowest. If that happens for any tiny interval surrounding that point, if that happens, then we call that a relative minimum. Okay, so this doesn't look like your everyday relative minimum. Usually you think about relative minimum as like this, but it's still possible to have a relative minimum that looks like this. Okay, or okay, you just need the point to be lower than everything else. Okay. All right, so that's going to be our relative minimum. +1 is relative minimum. Okay, is f double prime of -2 positive, negative, or 0? Okay, so at -2, right here, is this part of a smiley face or a frowning face? It's part of a frowning face, right? So in that case, f double prime is negative. So this answer would be negative. What about f double prime of 4, right? right here. F double prime of 4 is here. Now this is a straight line. Straight lines do not have any concavity. It's neither concave up or concave down. So in that case, it will be 0. Okay. What are the x-coordinates of the absolute maximum and absolute minimum? Okay, so what's the absolute maximum and absolute minimum? When you think about the absolute max and absolute minimum, endpoints are now included, and the lowest point of the graph happens to be this point here. So the absolute minimum happens when x is equals to -4. And the highest point is right here. This is slightly bigger than this, so that's the highest point. So absolute maximum would happen at x equals to -1. Finally, find the interval where f prime is less than 0. That means f is decreasing, right? If the derivative is less than 0, then f is decreasing. So let's erase some stuff here. Now, where is this function decreasing? I see that it's decreasing right here and also right here. Okay. Now, we can't say f prime is less than 0 at 1 because that's a point where f prime does not exist. So we really need to put open intervals from -1 to 1 and then 1 to 7, open intervals there. And then since you have two intervals, you have to put unions. So for this, you have to say -1 to 1, union, and then 1 to 7. That's what's needed. Okay. Question 37. Consider y equals to 6x to the 5th power minus 40x cubed plus 3. Find all critical numbers. To find critical numbers, you need to find the derivative. Critical numbers are where derivative does not exist or is equal to 0. In this case, derivative always exists, so we just need to know when this is equal to 0. Now, I see that all of these are divisible by 30 and also x squared. So if I factor the 30x squared, I get x squared times x squared is x to the 4th power, right? And then 30 times 4 gives you 120, so it's 4, just like this. And then afterwards, you have 30x squared, x plus 2, x minus 2. And I'm using the difference of two squares to factor this, right? A squared minus b squared is a plus b times a minus b. And I'm thinking of 4 as 2 squared, so it's plus 2 and minus 2. Okay, once I have this, then I have the critical numbers that which make each of these factors equal to 0. So 30x squared equal to 0 when x is 0, right? X plus 2 is equal to 0 when x is -2. X minus 2 is 0 when x is equal to 2. So you have 0, -2, and 2 as the critical numbers. So that's the answer to A. A is x equals to 0, -2, and 2. Okay, for each critical number, use the first derivative test to determine whether it is a relative max, relative minimum, or neither. Okay, so part B, you want to draw the number line, place all the critical numbers, -2, 0, and +2. And to use the first derivative test, you need to pick sample points. So we pick the sample point, I like -10, that's a big number. -1 and 1 should be a good number to pick between here. And I'll pick +10 here, okay? So +10, -10. And what we do with these sample points is to figure out the derivative at those places, because then you can figure out what's happening to f, whether it's increasing or decreasing, okay? Squared, and then -10 squared minus 4. So this is your y prime, right? So I'm just plugging in negative 10 to there, and that's 100, so 100 times 30, that's 3,000. And 10 squared is 100 minus 4, that's 96. And I don't have to multiply this because all I want to know is whether it's positive or negative. So that's definitely positive, so it's positive here. So f prime is positive here. And then f prime of negative 1 would be 30 times negative 1 squared. Negative 1 squared minus 4. So that's 30. And then 1 minus 4, that's negative 3. So that's negative. So it's negative here. F prime of positive 1 is 30 times 1 squared. 1 squared minus 4. Oh, that's again the same story. This is 30 times negative 3, so it's negative. So it's negative here. And then f prime of 10 is 30 times 10 squared. 10 squared minus 4, and that's same thing as 3,000 times 96. 3,000 times 96, that's positive, so it's positive. And what that means is for our f, it's increasing, decreasing, and decreasing more, and then increasing again. Okay. Now, if a function is decreasing and then decreasing afterwards, this is neither a relative max or relative minimum. So 0 is neither a relative max or relative min. But negative 2, the graph will be shaped like that, so it's a relative max. At positive 2, the graph will be shaped like this, so it will be relative minimum. Okay, so the answer to this, so for answer to B, we determined that negative 2 is relative max, and then 0 is neither a relative max nor relative minimum, and at 2 it's a relative minimum. Okay? All right. Now we have to find the intervals where the graph is concave up. That requires the second derivative, so let's remember that this is our y prime, 30x to the fourth, 120x squared, and differentiate that. Okay, so y double prime would be differentiating 30x to the fourth minus 120x to the squared, and you're differentiating it. 4 comes down, 4 times 3 is 12, 120x cubed. 2 comes down, minus 240x. And this time 120x is a common factor, so I factor that out, and you get x squared minus 2, because 120 times 2 is 240, right? And this one, although you can't factor this in the domain of reals. Oh, well, okay, so let's say this is our factoring. That's fine. So I want to know when this is equal to 0, because that can tell us when the concavity changes. So it's sort of like finding the critical number for y prime, because y double prime is the derivative of y prime. You're differentiating the y prime to get y double prime. You set that equal to 0. In turn will give you the critical number for y prime. Anyways, we need this in order to figure out when the graph changes its concavity. So either for this product to become 0, either 120x is equal to 0, which happens when x is 0, or x squared minus 2 is equal to 0, which happens when x squared is 2, and you take the square root of both sides and you get x equals to plus minus square root of 2. Okay, so what? So we have 0, positive radical 2, and negative radical 2 as points where f double prime is 0. And since f double prime always exists, and it's a continuous function, polynomials are continuous functions, it can never change its sign unless it hits 0. That means if we pick test points between these numbers, so I put negative 10, negative 1, positive 1, and positive 10, plug these test points into f double prime, then that can tell us whether f is concave up or concave down for the entire intervals. Okay, so we have 4 intervals. From each of these 4 intervals, I chose some random points. The simpler, the easier to calculate, so I chose the simplest numbers. So I take f double prime of negative 10. Let's see, what is that? It's 120. I'm going to use this formula here, okay? So it's 120 times negative 10 squared minus 2, which is negative 1200 times negative 10 squared is 100, 100 minus 2 is 98. And we don't really need to know the value, we just see that it's a negative times positive, so it's less than 0. Okay, so it's less than 0 in before negative radical 2. F double prime of negative 1 would be 120 times negative 1 squared minus 2. This is negative 120 times negative 1 squared is positive 1, 1 minus 2 is negative 1, right? So that's positive 120, which is positive. F double prime of positive 1 will give you 120 times 1 squared minus 2. That'll be 120 times negative 1, that'll be negative. F double prime of 10 would be 120, 10 squared minus 2. That would be 1200 times 98, so it'll be positive. So this is the result. F prime goes from negative to positive to negative to positive, which means that our function will be concave down, concave up, concave down, concave up. Okay. All right. So part C was asking for intervals where the graph is concave up. It's right here and here, right? So to get those intervals, I first write down the interval negative radical 2 comma 0 union, and then radical 2, after radical 2 it's concave up again, so it's radical 2 until infinity. So that's part C. And then D, what are the x-coordinates of the inflection points? Well, these are all points where the concavity changes, right? It went from concave down to concave up, concave, then concave down again, and then concave up again. So these are all inflection points. Right? So I have x equals to negative radical 2, 0, and positive radical 2. Right? Those are the answers. Question 38. Find the points of inflection and the open intervals on which the graph is concave up and concave down. Okay, so concave up, concave down means you need the second derivative. So let's differentiate this. Y prime is 4, and then log of x is 1 over x, so it's 1 over 2x, but because 2x is nested, you have to make a copy of that and differentiate. So that's going to be 4 minus 1 over 2x times 2, and then 2 cancels, and that's 4 minus 1 over x. Okay, then I differentiate this again, y double prime, which is 0. 1 over x differentiates to negative 1 over x squared, so this will become 1 over x squared. Okay, you can get this result just by using the power rule. 1 over x prime is x to the negative 1 prime, which gives you negative 1 times x to the minus 2. You subtract 1 off of negative 1, that's that. Okay, and negative 2 power means 1 over x squared. So that's the derivative of 1 over x. And using that, we can determine that that's your y double prime. Well, the thing is here, it's always positive, right? For all x, okay? And there's something that I should have done even before this. See, logarithms cannot take negative values. So the domain of this function is x bigger than 0. So you can't even call this x equal to 0 a critical number because it's outside the domain. Okay, and because of this, now we see that y double prime is always bigger than 0, which means this one is no inflection points, because it's always concave up. There's no change in concavity, so there's no inflection points. And concave up on the interval 0 to infinity. That's it. And there's no concave down. Okay, that's what we know about this 38a. Okay. So that was a rather simple question. Let's move on to the next one. For this one, we have to again find the second derivative. So let's try that. F prime of x is, you're differentiating a product, so you have to differentiate the first one, leave the second one untouched, but then in the second sum it's e to the negative 3x that gets differentiated and 8x gets untouched. Now 8x prime is 8, and e to the negative 3x, that's e to the negative 3x, because e to the x differentiates to e to the x, but then instead of x you have negative 3x. That means negative 3x is a inside function, it's a nested function, so we make a copy of it and differentiate. Negative 3x, x differentiates to 1, so you just get negative 3. Negative 3 times 8 is negative 24. So you have 8 times e to the negative 3x, okay, and then minus 24x e to the negative 3x. Okay, that's just the first derivative. We need to differentiate this again, but in order to differentiate again, it's better if you simplify this by factoring the e to the negative 3x out. So we factor that out, I get 8 minus 24x. You can also factor the 8 out, but I think this is easier. So I'll just simplify like this, and now we take the second derivative. Again, it's a product of two functions, so we have to use the product rule. You differentiate 8 minus 24x prime e to the negative 3x, plus you have 8 minus 24x times e to the negative 3x prime. And then if you differentiate 8 is 0, negative 24x differentiates to just 1. Okay. And then if you differentiate e to something, then it's the same thing, because e to the x differentiates to e to the x. Oh, I already said that, right? If you differentiate this, you get e to the negative 3x times negative 3. Okay. Now, let's try to factor e to the negative 3x out, because I do need to simplify. Then I get negative 24. And I get plus 8 minus 24x times negative 3. That's what's left after you take out the e to the negative 3x. And I think this one is e to the negative 3x. Let's see, negative 24. 8 times negative 3 is negative 24. Negative 3 times positive 24, that's 72. So that gives you e to the negative 3x, negative 48 plus 72x. And now we have to figure out when that's equal to 0 in order to find out where the interval of concave up and concave down is. So we set that equal to 0. So either negative 3x is equal to 0 or negative 48 plus 72x equal to 0. Well, exponential functions are never 0, so that can't happen, so it has to be this. Adding 48 both sides will give you 72x equals to 48. And divide by 72, I get 48 over 72. Now I know that 48 is 12 times 4, and 72 is 12 times 6. So after dividing top and bottom by 12, I get 4/6. And we can further simplify by dividing top and bottom by 2. So 2/3 is the only point where concavity may change. That's the point when f double prime is 0. So we know that 2/3 is a possible point where f prime can change its sign. And I'll pick two test points, 0 and 1, before and after, and evaluate f double prime at those points. Okay, so this is our f double prime. So what do I get if I evaluate f double prime of 0? This is e to the negative 3 times 0, negative 48 plus 72 times 0. E to the 0, this is 0th power. E to the 0th power is 1. So you end up with negative 48 plus 72, which is, let's see, 24, right? And that's positive. Okay, so it's positive. F double prime of 1 would be e to the negative 3, negative 48. Oh, I'm sorry. Here we plugged in 0, right? 0 times anything is 0. So this should be 0. So this is negative. Negative 48, that's negative. Okay. So this should have been, let me erase these. So, and erase this one. Okay, so this is negative 48, that's less than 0. So it's minus here, okay? Now on the other hand, if I plug in 1, this will be 72 times 1. I don't know what e to negative 3 is, but e to anything is always positive. And 72 plus negative 48, that's 24, so that's positive. So it's positive here. Okay, so 2/3 is definitely an inflection point because concave down, concave up, there's a change there. And so here's the result that we got so far. For this one, we get that 2/3, before 2/3, it's f double prime is negative, and after 2/3, f double prime is positive. So f is concave down before 2/3, concave up after 2/3. Okay, so that means x equals to 2/3 is an inflection. But whenever it says point of inflection, a point is a point on the coordinate axis. So you actually need the y-coordinate too. So you really need to plug this 2/3 into the function. F of 2/3 is equal to 8 times 2/3 times e to the negative 3 times 2/3, which is 16 over 3, and then e to the negative 2. E to the negative 2 is 1 over e squared, right? And then when you multiply fractions, top to top, bottom to bottom, so it's 16 over 3e squared. And because of that, we know that the inflection point, the only inflection point, is 2/3, comma 16 over 3e squared. And additionally, we know that concave up is after 2/3, so it's 2/3 to infinity, and concave down would be before 2/3, so negative infinity until 2/3. So that's the answer to all the questions for part B.